Hello everybody and welcome to this Module 4 Chapter 11 lesson. Today we are going to be going over transformations, symmetries, and tilings. To start off, we're going to start by going over question 1, and the question says, what type of rigid motion did Ephraim and Devontae use to transition the shape on the left to the shape on the right? So this lesson goes over different types of rigid motions, including rotational rigid motion and reflection rigid motion. And so we are going to be trying to determine which of those two was used to transform this shape on the left to this shape on the right. So when we think about reflection, we think about there being a line of reflection that you are going to flip the shape over. You're going to either reflect it over it or you're going to flip it from top to bottom. And so looking at this image, if we were to flip it over a vertical line of symmetry right here, the green triangles would still be on the top. They would just be facing the other way, and our trapezoid would still remain on the bottom. So it doesn't look like we're dealing with reflection rigid motion right now. When we talk about rotational rigid movement, we think about our shape being held by a certain point, and that shape is going to be moving around that certain point. So what I mean by this is that we are going to, for example, hold on to our shape right here, and we're going to rotate it this way about 180 degrees, and I just have a feeling that this is going to give us this shape that we have on the right. And so when we do this, this is called rotational rigid motion, and it involves moving an object just like that. And so the second part of this question says reflect the figure over a horizontal line through the center of the square. And so this involves our reflection rigid motion, like I was just talking about. We're going to place our horizontal line right through the middle of our square. And we know a square is identical on both sides, so it's not really going to change much no matter what we do to it. Remember, a reflection will have no turning or rotating. So this is important to remember because we are not going to be rotating it at all like we were in the first part of this problem. So when we flip our shape over our horizontal line right here, we are going to find our triangles are now on the bottom, but they are still facing the right. They're not facing the left anymore, which they were whenever we did rotation symmetry or rotation rigid motion a while ago. And so that is what our shape looks like. All right, moving on to number 2. Which of these images have one line of symmetry and no rotational symmetry? And so this kind of goes along with what we were talking about, rigid motions. A line of symmetry is present whenever you can place a line within an object and both sides of that object are going to be exactly the same. So for example, a square, you can place a line of symmetry right down the middle from corner to corner or horizontally down the middle, and it's going to be the same when you fold it in half. And so we are going to try and see which of these have a line of symmetry, but no rotational symmetry. Rotational symmetry is demonstrated whenever we have a shape that can be turned, maybe a quarter of a turn or a half a turn, and it looks exactly like the shape did in its original. And so we are looking for images within these that have one line of symmetry but do not have rotational symmetry. So I'm going to draw our lines of symmetry. Here they are. We can see that this diamond, the rectangle, the hexagon, they have more than one line of symmetry. They have 2 lines of symmetry and sometimes even more. So we are going to get rid of those because they have more than one line of symmetry. And they had rotational symmetry as well. If you turn this 180 degrees, you're going to get the exact same shape. And likewise with these two. So we are looking for no rotational symmetry. And of these last 3 shapes, there is one that still does exhibit rotational symmetry. So we're going to look at this by turning each one and seeing if we can notice if it makes the same shape before it makes it all the way back around. And so when we do this, we see that these first 2 don't have rotational symmetry. They don't make the same shape. But this triangle, it is an equilateral triangle, and if you turn it just 1 notch to the right or 1 notch to the left, you're going to get rotational symmetry, and it's going to be the same. So That leaves us with these two shapes that have a line of symmetry but no rotational symmetry. Okay, part B. Which of these figures has no line of symmetry but still does have rotational symmetry? So this is the opposite of what we were just doing. We want to find figures in here that don't have any lines of symmetry. That means we can draw a line. We can't draw a line anywhere. If we draw a line and see that it is the same on both sides, then that means it has a line of symmetry, and we are not looking for that right now. So when we draw our lines of symmetry, we see that the majority of these shapes do have lines of symmetry. So that really narrows down our options here. We're going to go ahead and wipe those out of here. So we're left with these two shapes right here. They're a little bit of unordinary shapes. They're not the shapes that you see every day. But we are wondering if they have rotational symmetry because they don't have any line of symmetry. It's odd to think about a shape still being somewhat symmetrical in a certain way, even though it doesn't have a line of symmetry. So we're going to do with these what we did with the last ones. We're going to replicate it, and this can be helpful if you are working on your test, if you have like cutouts of the shapes and you can actually see, or if you can move your test around to see, or your worksheet around to see if the shape has rotational symmetry, if it can be the same in a different way. We see that this does have rotational symmetry. If we turned that completely upside down, it would look the same as it did right side up. And we're going to see the same thing with this one. If we turn this shape upside down, it's going to be exactly the same as it was right side up. All right, number 3, is this figure a vertex figure? This question is kind of confusing, especially if you don't know what a vertex figure is. And so that's what I'm going to tell you right now. A vertex figure is made whenever you have a group of figures like this one on the right, and we are going to look at their interior angles. So we're going to look at these angles right here. And what we want to know is if the measurements of these 3 interior angles add up to be 360 degrees. If they add up to be 360 degrees, then this figure, these 3 shapes, are a vertex figure. And so to find this out, we are going to use our handy dandy interior angles formula, and that is n minus 2 times 180. And this gives us the total sum of the interior angles. So that's important to note because this is giving us the total sum of interior angles. Whenever we get this answer, that means we're not totally done with the problem yet. We need to take that answer, whatever sum we get right here, we want to divide it by the number of sides that we have within the object. We're going to divide it by n because n is equal to the number of sides within an object. And so we're going to go ahead and plug our sides into each of these, into this formula. So an octagon has 8 sides. We're going to plug in 8 for n minus 2. Multiply it by 180, we get 1,080 degrees. That means there's 1,080 degrees within all the 8 angles in this octagon. We're going to divide that by 8, and we get 135 degrees. So this red angle right here measures 135 degrees. That's just one part of our problem. We're going to do the same thing for the pentagon. We find that this angle, this green angle, is equal to 108 degrees. And for the hexagon, this little blue angle right here is 120 degrees. And so now we want to add up these 3 measurements. We get 135 plus 108 plus 120 equals 363 degrees. So close. We wanted it to equal 360 degrees. So that means that this figure is in fact not a vertex figure. All right, number 4, explain the relationships between the different shapes and angles within this figure. All right, this one can look complicated, but I promise it's not. So our shape right here, it kind of looks like a kite. It looks similar to a kite. And so we are going to look at the relationships between the angles and the sides and different parts of this kite. Is what we're going to call it. Okay, so the first part says, why is triangle QPT congruent to triangle SPT? So I'm going to kind of draw this out for us. Here is triangle QPT in black, and here is triangle SPT in blue. And so we want to know why these 2 triangles are congruent. These 2 triangles right here are congruent because they are exactly the same. They measure the same angles, they measure the same sides, they are the same, they are just facing 2 different ways. But Similarly, they have a line of symmetry right down the middle, and because we have this line of symmetry down the middle, we know that if we folded this kite right on this line of symmetry, both sides would be exactly the same. Both triangles would line up exactly with each other. There wouldn't be any overlapping or any edge hanging over or anything. And so moving on, why is angle QPT congruent to angle SPT? And so with this, we are looking at these angles right here. So this angle on the right and this angle on the left that are divided by the line of symmetry that goes right down the middle. And so we want to know why they're congruent. Well, this plays into our side angle side property. Our side angle side property tells us that if two sides of two triangles are the same, then the angle will be the same, and that means that those triangles are the same. Okay, next, why is triangle QPV congruent to triangle SPV? All right, I'm going to draw these out as well. Here is triangle QPV, and here is triangle SPV. We can see that these are just smaller portions of the first triangles we looked at. Because we know that our first triangles were congruent, we know that these are going to be congruent as well because it's just a smaller portion of those triangles. And also, we have these handy little blue tick marks and red tick marks at the bottom that tell us if there's one tick mark on this blue line, then that means there's another blue line that has one tick mark, and that means that they are congruent. Similar to the red lines, they have two tick marks, and that tells us that there is another line somewhere on this shape that has two red tick marks, and that is going to be congruent to that line. All right, and lastly, why is angle QVP a right angle? I'm going to just highlight that for us right here. Here's our right angle. This one is simple because we have this vertical line right here that can be our line of symmetry. And we also have this horizontal line that is 100% horizontal, and this line is 100% vertical. And when we have a horizontal and a vertical line that meet, we know that it is going to produce 90-degree right angles all the way around. So all of these angles right in here are going to be 90-degree angles. Number 5, find the measurement of angle NOQ. This problem can look very confusing because it just looks like a bunch of jumbled lines that they threw in a circle. I get it. It can be frustrating, but I promise it's not that hard. I'm going to go ahead and highlight our angle we're looking for in pink. So it's just going to be this small angle. So you can kind of get a hint that it's not going to be a very big angle that we're going to get. I'm going to highlight, oh, look at that. We have a pentagon in this circle. I didn't even notice with all the jumbled lines. Because we have a pentagon, we know that when we place the number 5 within our interior angle formula, it gives us the answer of 108 when we divide that by 5 and divide the sum of that by 5. And that means that each of these interior angles is 108 degrees. So angle N, angle E, angle P, angle A, and angle T are all 108 degrees. And so we can see angle N has this line going right through it that goes to our angle O that we're looking for. So, moving on. Oh, there's a triangle in our circle too. We know that an equilateral triangle has interior angles of 60 degrees. So that means all 3 of these angles within this triangle are 60 degrees. Well, would you look at that? Angle P of our triangle has our line for O going right through it. And the same with Q. We're going to take those lines away so that they're not so distracting. So we know that angle EPO right here is going to equal half of angle EPA because O goes right down the middle of angle P, and we know that angle EPA is part of the pentagon, which is 108 degrees. So EPO is going to be half of 108, which is 54. Because we know this, we know that we can deduce the measurement of angle NOQ by adding angles, or adding 54 to 50 plus 54. When we do this, we get that angle NOP is 108 degrees. Number 6, gives us quite a bit of information. It gives us this image on the bottom here, and it gives us some information. It tells us that Jenny is about 1/4 of a mile from a cliff. She is holding a ruler 2 feet in front of her face, and she can see that the cliff fits about in between 1.5 inches of the ruler. How about, the question asks us about how tall is the cliff? We have a lot of information here, and we want to find out how tall the cliff is, and we're not really given any direct information, but we are going to figure it out. We're going to use this relation, the distance from Jenny's eyes to the ruler over the distance between the ruler markings is equal to the height of the cliff over Jenny's distance from the cliff. And so when we do this, first we need to remember that 1 mile is equal to 5,280 feet. Because we're given different measurements, we're given feet and 1/4 of a mile and 1.5 inches, we want to convert all of these measurements into feet. And so when we do this, we find that our 1/4 of a mile that Jenny is standing away from the cliff is equal to 1,320 feet. And our the 1.5 inches that she can see the cliff between on her ruler is equal to 0.125 feet. So now that we've transferred everything to feet, we can plug it into our formula and get the height of the cliff over 1,320 feet is equal to 0.125 feet over 2 feet. And so we still have a variable here on top. So what we're going to do is make that equal to the inches times the feet, or the feet times the feet. 0.125 times 1,320 over 2. When we do this, we get that the height of our cliff equals about 83 feet. It's a little under 83, but we're going to round up because it's asking us about how tall is the cliff. So the height of the cliff is about 83 feet. And that is it. Thank you for watching.